how this is used in some examples. So now let's see this process, this Gaussian elimination process. So example 8, solve this system, and I like to call my rows are row 1, row 2, row 3, and I'm doing this so I can keep track of my row operations as I'm going through. So remember, we're only trying to use those 3 operations above. So I'm going to start this process off by, I'm going to add row 1 and row 2, and I'm going to change that to my no row 2. So x minus 2y, the first equation stays the same. The second equation, I'm going to add these 2 rows, minus 2y plus 3z equals 9. Negative x plus 3y equals negative 4. So now my second row is going to turn into y plus 3z equals 5. My third row is going to stay the same. Now see, we're almost there for the staircase pattern. So now we need to eliminate this 2x here. And I'm going to do that by multiplying the first row by negative 2, adding it to row 3, and changing that to my new row 3. Remember, we want to change it to, oh, not here, sorry. My first equation stays the same, x minus 2y plus 3z equals 9. Second equation stays the same, equals 5. And I was saying, remember, we're trying to have the same coefficient, different signs, and when we're trying to do the elimination method. So negative 2, that's negative 6z equals negative 18. Let me make sure I don't forget that negative. And then the third equation is 2x minus 5y plus 5z equals 17. Adding those, I'll get negative y minus z equals negative 1. So now I need to get rid of this negative y. Luckily, the coefficients are the same, just add opposite signs. So I'm just going to add row 2 plus row 3 and change that to my new row 3. So the first 2 equations stay the same. Let me put that here. Oh, that's not supposed to be an image, but okay. And then my new equation is y plus 3z equals 5. Negative y minus z equals negative 1. 2z equals 4. But remember, in row echelon form, we need to have the leading coefficient of 1. So I'm going to divide row 3 by 2, or same thing as dividing by 1/2, and changing that to my new row 3. So now, let me paste that one. My new row 3 then is z equals 2. Awesome, we got it in row echelon form, staircase pattern, coefficients of 1, excuse me, and therefore this is in row echelon form. But that wasn't what they were asking. They were asking us to solve for that equation. Now, the solution to this row echelon form is equivalent to our original equation. So if we back substitute, we should be able to solve this system. So if z equals 2, then y plus 3 times 2 equals 5. Y equals negative 3 times 2 is 6, divided minus 6 on both sides. Y is negative 1. And if y is negative 1, then x minus 2 times negative 1 plus 3 times 2 equals 9. X plus 2 plus 6 equals 9. Therefore, x has to be 1. Meaning, my solution for my actual system is 1, negative 1, and 2. And there you have it. Now, visually, this can be represented as, since this is a system of planes, their intersection would be something like the picture below in the next page. See, these planes are intersecting, and their intersection point where the three of them intersect is going to be at 1, -1, and 2. Notice it's very similar to the two-dimensional one when we have x and y. It's their intersection point. Now, for example 9, we're going to see a different type of solution. So let's see. Example 9 is, let me fix this. This should be a -2. All right, there you go. And we're going to start this off by first eliminating this first term of the second row. And we're going to do that by multiplying the first row by -2. Remember, we wanted to have the same coefficient, different signs. When I add it to row 2, I'm going to make that my new row 2. So first equation stays the same. Minus 3x2 plus x3 equals 1. Over here, I have -2 times the first row, -2x1. Let me give myself some more room over here. -2x1 plus 6x2 minus 2x3 equals -2. 2x1 minus x2 minus 2x3 equals 2. Those go away. So my new row 2 is 5x2 minus 4x3 equals 0. And my third equation is going to stay the same for now. x1 plus 2x2 minus 3x3 equals -1. And as we did at the beginning, we're going to now try and get rid of the first term of the third equation. And how do we do that? In this case, we're going to multiply -1 to the first row and add it to row 3 and make that my new row 3. So instead of copying the rewriting, let me copy and paste. So the first two rows stay the same, and we said negative times the first row, so -x1 plus 3x2 minus x3 equals -1. Added to the third row, minus 3x3 equals -1. That'll give me 5x2 minus 4x3 equals -2. So, I don't want to. I'm gonna keep going. Now I'm gonna get rid of the first term of the third row. Now we do that by just multiplying negative to the second row, add it to the third row, and make that my new third row. So the first two rows stay the same. Paste. Now my third row, if I add straight up and down, the first term will go away, 0. And then I have, let me write this out, -5x2 plus 4x3, 5x2 minus 4x3 equals -2. If I add these, I'm going to get 0, 0, -2. 0 equals -2. Now here is the problem. This is the false statement. And we've seen this before. When it's a false statement, that means there is no solution. So we just seen an inconsistent system. Same as inconsistent. And there we have our solution. Okay, no solution. Now the picture with this, so graphically, what would this look like? This would be planes that maybe two planes may intersect, maybe two planes intersect, but they all won't intersect at one point. This would be planes that may have two intersecting planes, but not all three. Well, what would it look like in the case of infinitely many solutions? Well, in the case of an infinitely many solutions, that would look like, let me see a different color. In the case infinitely many solutions, it would again parallel would be, sorry, not parallel. Parallel means no solutions. That also could be the case for this one above. They could have been parallel planes. Let me write that up. And in the case of no solution, infinitely many solutions, they would be the same planes or scaled factors. Awesome.